So let's now move on to the topic of optics. In this video, we take a look at the concept of light as an electromagnetic wave and at the reflection and refraction of light. It has been shown that light is an electromagnetic wave, so much so that as far as our course is concerned, when we say light, we're talking about electromagnetic waves, and when we say electromagnetic wave, we're talking about light. Light is an electromagnetic wave. An electromagnetic wave is basically a traveling wave of electric and magnetic fields coupled together and moving as one. It's better to think, or at least more convenient to think of light as being comprised of two waves. You have an electric field wave and a magnetic field wave. These two waves make up the components of the electromagnetic wave. They are coupled together and moving, coupled together or tied together and moving with the same speed v. The electric field component and the magnetic field component of the wave are perpendicular to each other. They are 90 degrees with respect to each other. For instance, in this figure, the electric field component or the electric field wave is lying on the xy plane, while the magnetic field component is lying on the xz plane. They are perpendicular to each other. Unlike a mechanical wave like wave in a string or sound wave, an electromagnetic wave do not need a medium in order to exist and propagate. A light wave can travel in vacuum. In vacuum, electromagnetic waves always travel at a constant speed c. C is equal to 3 times 10 to the 8th power meters per second. The different spectra or types of light include long waves, radio waves, which basically are radio and television transmissions. You have infrared light, visible light, ultraviolet light, X-rays, and gamma rays. So these are all examples of light. Since light is a wave that travels in all directions from the source just like sound, you have a light source. If you turn on the light source, light will travel away from the source in all directions. Since light is a wave that travels in all directions, we can use the same equation for intensity that we had for sound waves. Wave intensity I is also given by I is equal to power of the source divided by the surface area upon which the wave is spread out. So I is equal to P over A. For instance, in this figure, light travels away from the source in all directions. So basically, the surface area is spherical. And the surface area for the sphere is 4 pi r squared. So I is equal to power over surface area for a spherical surface area. I is power over 4 pi r squared. If we take the intensity I1 at point 1 and intensity I2 at a different point 2 and then divide I1 by I2 using this equation for I1 and I2, we get what is referred to as the inverse square law. I1 is equal to I2 R2 squared over R1 squared. Again, I1 is intensity at point 1 and I2 is intensity at point 2. For a more complete picture of the behavior of light, you might want to read up on the concept of the Doppler effect of light. So you might want to consider this as a reading assignment, the Doppler effect of light. What happens when both the source of the light wave and the listener are moving with respect to each other? We have what is referred to as the Doppler effect of light. Next up, we take a look at the reflection of light. When you have two media, medium 1 and medium 2, there's a border between the two media. We refer to that as the interface between the two media. When light is incident upon that border, that interface, two things may happen. The light will either bounce off, we refer to this as the reflection of light, or the light will pass through. We refer to this as the refraction of light. Or both will happen at the same time. Part of the light bounces off and the remaining part will pass through. When light bounces off the interface, so you have incident light and it bounces off or reflects off the interface, we have the law of reflection. Theta 1, angle of incidence. Theta 2, angle of reflection. Law of reflection tells us the two angles are equal. Theta 2 is equal to theta 1. The angle of reflection is equal to the angle of incidence. On the other hand, for refraction of light, the incident light, when after it strikes the interface, the light passes through, you have refracted light. Because of the difference in the two media, the light, instead of simply traveling in a straight line, the light will appear to bend. The bending of light as it passes through one medium to another is what we refer to as the refraction of light. And when light is refracted, it is subject to the law of refraction, or what is referred to as Snell's law. You have angle of incidence theta 1, angle of refraction theta 2. Just like with reflection, the angles are based on the normal line or the line perpendicular to the interface. N2 sine theta 2 is equal to N1 sine theta 1, where N1 is the index of refraction of medium 1 and N2 is the index of refraction of medium 2. The index of refraction may be considered, or is basically rather, property of the medium. Each medium will have a corresponding value of the index of refraction. So you have N1 and you have N2. The index of refraction is basically the ratio between the speed of light in vacuum and the speed of light in the medium. So kung medium 1, N1, speed of light in medium 1. And therefore is just equal to C divided by V. Here are some examples of some values of the index of refraction. You have index of refraction of vacuum, index of refraction of air, and index of refraction of water. As you can see, index of refraction is a unitless quantity. It does not have any unit. Speed divided by speed, the unit cancels out. Refraction of light is also referred to as the transmission of the wave from one medium to another. So that when you see the term transmission, for the most part, as far as our course is concerned, this means refraction. Frequency of light has been observed to be unaffected when light transmits from one material to another. So when light passes through from medium 1 to medium 2, the frequency of light here is just the same as the frequency of light in the other medium. The frequency of light is unaffected by the medium change. What is affected is the wavelength as well as the speed of light. Light is basically a periodic wave, so we can use the equation for the speed of a periodic wave. V is equal to F lambda. If we isolate F is equal to V over lambda. Since frequency is unaffected by the medium change, F1 is just equal to F2 is just equal to F3 and so on. Frequency in medium 1, frequency in medium 2, frequency in medium 3, and so on. Meaning, V1 over lambda 1 is equal to V2 over lambda 2 is equal to V3 over lambda 3 and so on. We get the following relationship. V1 over lambda 1 is equal to C over lambda C. Rearranging, we can get another equation for the index of refraction. N is equal to C over V is equal to lambda C over lambda V. Lambda C, wavelength of the light as it travels in vacuum, while lambda V, wavelength of the light as it travels through the medium. Under certain conditions, the refraction of light that should normally happen does not happen. Light that should normally refract does not happen. Instead, total internal reflection occurs. Let's take a look at under what conditions the total internal reflection will occur. So before that, there's a slight correction here. It should be refraction of light that should happen does not happen, or light that should normally refract does not happen. So you can take out refraction here from this statement if you want to. So you have light, incident light. If we set the angle of refraction to 90 degrees, no light passes into the second medium. So there's no refraction of light. Instead, the light will be reflected. If we now use yung theta 2 equal to 90 degrees in our equation for the law of refraction, we get the following relationship. Theta 1 is equal to inverse sine of N2 over N1. We refer to this angle as the critical angle. So let theta 1 now be equal to theta C. The critical angle at which total internal reflection happens. Also note the following. Sine function for inverse sine of N2 over N1 for this expression to give you an answer, N1 must be greater than N2. Otherwise, if N2 is greater than N1 and you try to input this into your calculator will give you an error result. So for this expression, not to give you an error result on your calculators, N1 must be greater than N2. Which means we have two conditions for total internal reflection to happen. One, the angle of incidence, theta 1, must be at the critical angle theta c. And the combination of N1 and N2 must be that N1 must be greater than N2. For a more complete picture of the refraction and reflection of light, please consider the following reading assignment. Multiple index of refraction. Normally, materials have only one index of refraction, but some materials have more than one index of refraction. So, multiple index of refraction. Also, you might want to look into the concept of polarization of light and polarization by reflection. So that's it for now. In the next video, we'll talk about or we'll look into the concept of image formation using lenses and mirrors. Well, basically, image formation. How light is used to form images. So thank you for watching.